Thing, like Tesla.
Okay, Tesla fans, today we're going to look at 3 different ways of analyzing the same circuit. Well, pretty much the same circuit. So you can see a diagram of the circuit we're going to look at here. Very simple, about as simple as you can get and still have something to analyze. So here's something I've been experimenting with. I'm trying out different ways of putting together circuits, prototyping circuits. So this is a paper circuit kind of concept, even though it's on plastic. We've got some conductive tape. We've got conductive paint holding the LED in place, and you can see the battery there on the left side. You can tell the positive is on the top because that's the longer line. You take the 2 parts of the plus sign and you stack them together, and it's longer than the minus sign. So that's how you can tell the plus is on top. Now, in the diagram, the 2 conductors there are not connected. So in the first way of looking at a circuit, which is steady state or DC, it's not connected at all. So what we have to do to make the current flow is actually attach an ammeter there. And in the experimental setup, we can see about 5 milliamps or so flowing through the circuit. So we can talk about the pipe analogy again. We can continue that from our previous discussion about Tesla's big secret. But in the DC case, there's really not a lot going on. But as long as we're talking about DC, a few things are worth mentioning here. Volts and amps. You hear these thrown around a lot. What are volts and amps? A volt can be compared to water pressure. That's a pretty easy analogy, but what is it really? It's a little bit more abstract. A volt is the potential between 2 points in the circuit to push charges around. Electrons are negative charges, and we're pushing them around. Nothing can create or destroy any charges, not even black holes. All we can do is push them around our circuit. So a volt is the amount of potential or pressure that, if made to flow with 1 amp of current, would produce 1 watt. Okay, so what's that mean? So you don't have to memorize any of this. I'm going to go through this really quickly. I just want to give you an idea of how these things are equivalent to everyday mechanical things, like lifting up a 1 liter bottle of water. It weighs about 1 kilogram. So a watt means 1 joule per second. Well, what's a joule? A joule is 1 Newton meter. 1 Newton is a measure of force across a distance. And what's a Newton? Well, that means accelerating 1 kilogram, so that like that 1 liter water bottle, at about 1 meter per second per second. So in 1 second, accelerating it from, say, 0 to 1 meter per second. Everything equates down to physical measurements that you could do with an everyday scale and things like that. So what's an amp? So an amp is much more concrete. There's a particular large number called a coulomb, and if that many electrons are flowing past a particular point in a second, that means that's 1 amp of current flowing. What you want to keep in mind is, in a circuit, if you're going to measure voltage, it's always relative from point A to point B. Current is always in a line. So normally that means you have to interrupt the circuit, like we did here in our DC circuit. Right? And the current will be the same throughout the entire circuit, right? Because the charges cannot be created or destroyed. They can't leak from our pipes, because we're talking about a steady state system here. If you can measure the current in one part of the circuit, it'll be the same in another part of the circuit. It can split off into 2 different sub-circuits, and they can join back together. But overall, the total current will be constant. Okay, the second way of thinking about a circuit, or at least analyzing it, is alternating current, AC. So we got the simulated circuit up here in our laboratory. Got a 5 hertz signal going here, and it's going through a resistor and a capacitor. It's an RC circuit. So if we want to look at what this looks like, here's the voltage on the scope here, coming in. Here's the voltage across the resistor, and here's the voltage across the capacitor. Now, let's pause this and take a closer look at what's happening here. All right, something interesting is happening here. So the signal's here, the resistor is here, so it's lined up with the resistor. The voltage across the resistor and the voltage across the signal are in phase. But across the capacitor here, it's 90 degrees out of phase. So right when this is hitting its peak, this is at a 0, and when this is hitting a 0, this is at its peak. And the reason for this is because the capacitor is, let's look at the water pipe analogy again for that. So I'm going to refer to this article on Quora here. I'll put the link in the notes. So if this pump is pushing, it's distorting on the diaphragm here. It's pushing it. It can only go so far though. But when we're talking about alternating current, it starts pushing the other way, so the diaphragm can flex back and forth, and it can allow, effectively, a current to flow, even though no water is actually flowing all the way through. But by and large, it is analyzable because we have the luxury of assuming that our current, that our signals are staying inside the wires. Which leads us to the third way of analyzing the circuit. RF. RF gets crazy because you no longer can assume that the signals are staying in the wires. Things can fly all over the place, and it can cause all kinds of confusion and misunderstandings. If you think the circuit is going to behave like an AC circuit that we saw before, or like a DC circuit, you may be completely mistaken. Two things could be connected with a wire and not have current flowing between them. Two things could be not connected at all and still having RF flying around. Here's another link I will give you. This is my own website, the Antenna Project. I tried to explain how a simple dipole, means two wires like we saw in our schematic diagram, how that works. All right, so it starts off with a basic circuit like the one we saw before. Again, positives on top. It's the longer one. We talk about what happens if you start switching this on and off. Talk about the right-hand rule. Talk about charges. What it ends up with is this. So we're feeding a signal in at the feed point here, and the signals are going out through these two wires. The length of these wires are tuned so that it is a total of half of a wavelength of whatever the frequency is that we're putting into it. Right? So speed of light, every AC frequency has a particular wavelength. You can make an antenna that matches that wavelength. And in fact, for it to be an efficient antenna, it has to be matched. The current at different points along the antenna here actually drops. It's highest at the feed point, and the current drops down to 0 at the very end. So this completely violates the rule we just talked about for AC or DC, where the current is the same throughout the circuit. Now we have different currents because there's energy flying around in radio waves. Right? There's an electric field. The voltage is the opposite of this. The voltage is highest at the ends of the antenna and pretty much 0 at the feed point. That creates an electric field between these. The combination of the electric field and the magnetic field creates an electromagnetic wave. And these things split off from the antenna and they go flying out through space. So that's how antennas work. And it can work in exactly the opposite way too for a receiving antenna. Take that water pipe analogy we've been using, crumple it up, throw it in the garbage. It doesn't work for RF. Tesla, on the other hand, he had an intuitive understanding of this. Me, not so much. So that's why we're here. We're going to figure this out together, and we're going to put together the pieces.
Teslanomicon.
Today's book recommendation is Electronic Gadgets for the Evil Genius, second edition, of course, by Bob and Ani. So if you want to build Tesla coils, all kinds of crazy things in here. Plasma, arcs, lasers, Jacob's Ladder. This is the book. This is fun just to page through and just to get some ideas about things that you might want to build. So if you're into making, check out this book.